Newton's grasp of gravity was advanced enough to enable humanity to journey from Earth to the Moon. But have you ever found yourself lost in the relentless passage of time, contemplating whether our current understanding is merely the surface of a much larger temporal iceberg? Newton's insights were not just theoretical. They represented a key that could potentially unlock the secrets of the cosmos, revealing a universe far more complex and inspiring than we ever dared to imagine. Brian Cox's new theory presents a challenge to our conventional perception of time and its implications for our understanding of reality. This theory invites us to embark on an intriguing exploration through the corridors of time itself, diving into the recent groundbreaking concepts introduced by Brian Cox regarding the nature of time within the vast universe. Mysteries await discovery, particularly those relating to time and gravity, which are crucial to our existence. Picture a world where time behaves unusually, where it can either slow down or accelerate. Additionally, the force that keeps us grounded might not be what it appears to be. This is the domain of Albert Einstein's theories of relativity, where our comprehension of time and gravity takes on a peculiar twist. Einstein, a prominent figure in physics, offered us a new perspective on the universe through his theories of relativity. His work established the groundwork for understanding how time behaves under various conditions, especially at extremely high velocities. The journey began in the early 20th century when Einstein introduced two revolutionary theories: the special theory of relativity and the general theory of relativity. Published in 1905, the special theory of relativity transformed our comprehension of time and space. In essence, it asserts that the laws of physics remain consistent for all observers who are not accelerating, regardless of their motion. This theory introduces the concept of relativistic effects, including the well-known idea that time can dilate or slow down under certain circumstances. One intriguing experiment used to illustrate time dilation involves a light clock. Imagine being inside a spaceship moving nearly at the speed of light. Inside this spaceship, a beam of light bounces between two mirrors perpendicular to the direction of motion. According to the principles of physics, the speed of light is constant for all observers, so the light beam appears to travel diagonally. For observers inside the spaceship and those outside it, the time it takes for the light beam to complete its journey should be the same. However, since the path is longer for the outside observer, it seems as though it would take more time for the light to finish its journey. This perceived time difference between the two observers is what Einstein referred to as time dilation. Essentially, time slows down for the observer in motion compared to the stationary observer, meaning that time behaves differently based on your motion. Understanding these relativistic effects is not merely a theoretical exercise. Scientists use large machines, such as particle accelerators like the Large Hadron Collider, to propel particles to nearly the speed of light. When particles move at such velocities, time must be considered in a special way to make accurate predictions and measurements. Albert Einstein's special theory of relativity, proposed in 1905, altered our view of the universe, particularly regarding time and movement. This theory challenges our intuitive assumptions, stating that the rules of physics are the same for everyone, regardless of their speed. Unlike everyday experience, where adding more speed seems to increase velocity, Einstein's theory posits a maximum speed that nothing can exceed, the speed of light. Consequently, events that appear simultaneous to us might not seem so for those moving close to the speed of light. Another outcome of this theory is length contraction, where objects in motion appear shorter in the direction of movement from a stationary viewpoint. Additionally, the famous equation E=mc² emerges from this special framework, demonstrating that energy and mass are interchangeable. This principle is crucial for understanding the behavior of fast-moving particles and phenomena like nuclear reactions. In practical terms, special relativity is more than a theoretical concept. It has applications in everyday technology such as GPS satellites, which are in constant motion, experience time differently. If we did not account for this time dilation effect in GPS calculations, navigation accuracy would be severely compromised. Thus, special relativity teaches us that time is not uniform for everyone. It varies based on motion. This challenges our conventional views of time and space, suggesting that our usual understanding of the universe might be slightly off. According to the special theory of relativity, Time is not fixed but influenced by motion. Fundamental principles like the constancy of the speed of light and the connection between energy and mass have been confirmed through numerous experiments. Einstein's general theory of relativity, introduced in 1915, delves deeper into the relationship between gravity and the structure of the universe. It disrupts the traditional notion of gravity as a mere force pulling objects from a distance, proposing instead that gravity results from the curvature of space and time. This theory presents gravity not as a mysterious force but as a natural consequence of the way objects move through the universe. In general relativity, the universe is viewed as a four-dimensional entity, combining three spatial dimensions with one of time. Massive objects like stars and planets affect the shape of space and time around them, which we perceive as gravity. Imagine space-time as a large, flexible blanket. Placing a massive object like Earth on this blanket creates a depression, causing smaller objects placed nearby to roll toward this dent. This depiction illustrates how general relativity explains gravity not as an enigmatic force but as a response to the bending of space-time. General relativity provides a robust framework for understanding planetary motions in our solar system. For example, it accurately describes the elliptical orbits of planets around the Sun. This differs from the older notion of gravity, which struggled to explain planetary movements. The newer perspective that space and time are curved fits better with observations. A significant confirmation of general relativity occurred during the solar eclipse of 1919, when Sir Arthur Eddington's team observed how light from distant stars bent around the Sun. The results matched Einstein's predictions, validating his theory. Just as motion can alter our experience of time according to special relativity, gravity also influences time. In regions with strong gravity, time progresses more slowly compared to areas with weaker gravity. For instance, if you were near a massive object like a black hole, your clock would tick more slowly than one positioned farther away from this intense gravitational field. General relativity also introduces black holes, regions where gravity is so strong that not even light can escape. The boundary around a black hole is called the event horizon, marking a point of no return. Once an object crosses this threshold, it is drawn into the black hole with no possibility of escaping. Initially, Einstein added a cosmological constant to his equations, assuming a static universe. However, upon discovering that the universe is expanding, he considered this addition a major error. This concept of an expanding universe, derived from general relativity, is a cornerstone of the Big Bang theory, which explains the universe's origin. Additionally, general relativity predicts the existence of gravitational waves, ripples in the fabric of spacetime caused by massive objects moving rapidly, such as when black holes or neutron stars merge. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, further confirming Einstein's theory. Over time, numerous tests have validated general relativity, whether by observing planetary motions, bending starlight, or detecting gravitational waves. While the idea of gravity being a fallacy might seem surprising, especially given our daily experiences with it, it is normal in physics to question and explore alternative theories. Researchers like Brian Cox often challenge established ideas, and there are discussions about alternative perspectives on gravity. One such idea, known as modified Newtonian dynamics, MOND, proposes that gravity behaves differently at low speeds, particularly in galaxies, without invoking dark matter. Instead of introducing unseen matter, MOND suggests that gravity becomes stronger at lower speeds. The gravity debate also involves dark matter and dark energy, introduced to explain certain cosmic phenomena. Critics argue that alternative theories might account for these observations without requiring dark matter. Researchers like Eric Verland propose ideas such as emergent gravity, suggesting that gravity could emerge from fundamental principles of the universe's structure and interactions. This perspective views gravity as a secondary effect of more fundamental quantum forces, similar to how temperature results from the movement of particles in a gas. This challenges the traditional view of gravity as a fundamental force, suggesting it could be a complex phenomenon arising from underlying interactions. If validated, this concept could revolutionize our understanding of the universe and its fundamental forces. Another perspective considers gravity as a local interaction rather than a force acting from a distance. This theory proposes that what we perceive as gravity might result from the exchange of hypothetical particles called gravitons. These particles would mediate gravitational interactions, akin to how photons mediate electromagnetic forces. Although gravitons have not yet been detected, their existence would align with quantum field theory principles and provide a quantum-level explanation for gravity. In the realm of quantum gravity, efforts are focused on reconciling general relativity with quantum mechanics. Traditional views of gravity as a continuous force break down at extremely small scales, such as near the Planck length. Quantum gravity theories aim to understand how gravity operates at the quantum level and its relationship with other fundamental forces. In this context, gravity is seen as a force arising from fundamental particle interactions, offering a new perspective on its nature. Brian Cox's recent theory offers a compelling perspective on time and gravity by integrating cutting-edge research and exploring new concepts. His ideas illuminate the fundamental forces shaping the universe while challenging conventional notions. These theories present exciting possibilities for understanding reality. Join us as we delve deeper into the complexities of time and gravity, unraveling the mysteries of our universe. Embrace the intellectual journey and explore the fascinating world of Brian Cox's groundbreaking theories. As we delve further into the implications of Einstein's theories, we encounter intriguing extensions and modifications that seek to address the limitations of his original ideas. One such extension is the theory of quantum gravity, which attempts to reconcile general relativity with quantum mechanics. While general relativity excels at explaining large-scale phenomena, such as the movement of planets and the curvature of spacetime, quantum mechanics governs the behavior of particles on the smallest scales. Quantum gravity aims to merge these two frameworks into a unified theory, providing insights into how gravity operates at the quantum level and offering a more comprehensive picture of the fundamental forces. Among the leading approaches to quantum gravity is string theory. This theory posits that the fundamental constituents of the universe are not point-like particles but rather one-dimensional strings that vibrate at different frequencies. String theory proposes that these strings interact in a multidimensional space, which can potentially explain the behavior of gravity at the quantum level. However, string theory remains a work in progress, with many of its predictions yet to be tested experimentally. Another promising approach to quantum gravity is loop quantum gravity. This theory suggests that spacetime itself is quantized, composed of discrete units or loops, rather than being a smooth continuum. Loop quantum gravity aims to describe how spacetime evolves at the smallest scales and how it interacts with quantum particles. While still in its developmental stages, loop quantum gravity offers a potential framework for understanding the quantum nature of gravity and its implications for our universe. In addition to these theoretical advancements, observational techniques continue to push the boundaries of our understanding. The Event Horizon Telescope, EHT, collaboration, for example, has provided the first direct image of a black hole's event horizon in 2019. This groundbreaking observation of the supermassive black hole in the galaxy M87 has offered new insights into the nature of black holes and the validity of general relativity in extreme environments. The data from the EHT has also opened up new avenues for testing theories of gravity and exploring the behavior of spacetime near these enigmatic objects. Moreover, gravitational waves, ripples in the fabric of spacetime predicted by general relativity, have become a key focus of observational research. The Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo collaborations have detected gravitational waves from merging black holes and neutron stars, providing empirical evidence for Einstein's predictions and offering a new way to probe the universe. These detections have not only confirmed aspects of general relativity but have also led to the discovery of phenomena such as kilonovae, explosive events resulting from neutron-star mergers, which produce heavy elements like gold and platinum. In parallel with these advancements, there is a growing interest in exploring the concept of emergent gravity. This idea suggests that gravity is not a fundamental force but an emergent property arising from the collective behavior of underlying quantum degrees of freedom. According to this perspective, gravity might emerge from more fundamental interactions or principles, such as entropy or information theory. This approach challenges traditional views of gravity as a primary force and offers a fresh perspective on how the universe operates at its most fundamental level. Furthermore, the study of dark matter and dark energy continues to be a major focus of research. While dark matter was originally introduced to explain the discrepancy between observed and expected gravitational effects in galaxies, its true nature remains elusive. Several experiments and observational campaigns are underway to detect dark matter particles directly or indirectly, such as those involving cryogenic detectors or particle colliders. Similarly, dark energy, responsible for the accelerated expansion of the universe, remains a major mystery. Researchers are investigating its properties through observations of distant supernovae, galaxy clusters, and the cosmic microwave background. Additionally, the concept of extra dimensions has captured the imagination of theoretical physicists. Some theories propose that the universe may contain additional spatial dimensions beyond the familiar three. These extra dimensions could potentially explain various phenomena, such as the weakness of gravity compared to other fundamental forces. The Large Hadron Collider, LHC, and other high-energy experiments aim to probe these possibilities by searching for evidence of extra dimensions or deviations from known physical laws. The ongoing exploration of the universe's fundamental aspects invites us to reconsider our understanding of time and gravity continually. As new theories emerge and experimental techniques advance, we are constantly refining our knowledge and challenging established notions. The intellectual journey into the depths of space-time and fundamental forces offers not only a profound appreciation of the universe's complexity, but also a sense of wonder and curiosity about the mysteries yet to be unraveled. In summary, the investigation of time and gravity encompasses a rich tapestry of theoretical and observational endeavors. From the groundbreaking theories of relativity to the latest advancements in quantum gravity and the exploration of dark matter and energy, the quest to understand the fundamental nature of the universe remains a vibrant and evolving field of study. As researchers like Brian Cox and others continue to push the boundaries of knowledge, we are invited to engage with these ideas and explore the profound implications they hold for our understanding of reality. The journey into the depths of time and gravity is not just a scientific pursuit, but a quest to uncover the fundamental truths that shape our existence.